on, and this now is very much going to become your friend. So if you look in this table in the back of your book on page 1088, this is going to become a page that you're going to reference a lot, okay, in the near future. You might want to put a little bookmark here or something. So you're going to have 3 columns. The first column is what we're going to talk about today, which is delta H naught. So what this stands for is what's known as the standard enthalpy of formation. So this is a very, very specific definition. So these values are associated with how you could make that compound, and this is important, from its elemental substances. So for example, you look at water. There's a whole bunch of different ways you can make water. You can take hydroxides and heat them up and get a byproduct of water. You can take sodium chloride and or hydrochloric acid and sodium hydroxide and make water that way because you get salt water, okay? You can take hydrogen and oxygen and blow it up and get water that way. So to make it like a standard thing on how this works, this is why it's called the standard enthalpy of formation. It's only the values associated with how you make it from its elemental substances. There's more than one way to make a lot of these. This is just from its elemental constituents. Now, the second column is delta G naught. We'll get into that. That's your change in Gibbs free energy. We've talked about that, okay? So the second column is your Gibbs free energy. The third column is what we'll get into tomorrow, what's known as entropy, which is the amount of disorder in the system. So a couple of things about units. Your delta H and your delta G, those are in kilojoules per mole. So the first 2 columns, same units, kilojoules per mole. The third column, which is entropy, that has different units. Those are joules per mole Kelvin. So joules per mole Kelvin, that third column, is completely different than the first 2, okay? So we're eventually going to use information in an equation that involves all 3 of these. So you have to pay attention to the entropy ones. Is this thing spazzing out?
Yeah, it was flashing.
Oh, so annoying. So that third column, I'm just going to plant the seed now. Pay attention to that third column, has completely different units than the first 2. Now, if you go down here, and it gets a little bit weird. If you look at, when we're going to spend a lot of time talking about water. So water, oddly enough, and these are kind of grouped by different elements. Water is actually listed over on page 1090 under the oxygen column, okay? Don't know why, they've just always done it that way. So when you're looking for water, you have to find the oxygen column. So a couple of things about water. We talked about this yesterday. Notice with the water, you have 2 different thermodynamic properties. One as water as a gas, and one as water as a liquid. They're completely different thermodynamic values, okay? So this is why when you say, hey, we're going to make water, what form is that water in? Because that's going to determine which thermodynamic column that you use. So make sure, especially on that water, that you pay attention to what those values are. Now, if you look at that oxygen column, this is true for all of these. Some of these, like oxygen gas, has a delta H of 0. Same thing with like phosphorus, the elemental forms of all of these are 0. So the elemental forms of these have 0, mainly because of the fact that that's what it is. It's the elemental form. We're not making it. So the standard enthalpy of formation for elemental substances is 0. So very similar to when we looked at like the thermodynamic or the on the reduction chart, the reduction of hydrogen was defined as 0. Okay, that's what's happening here. So if it's the elemental form, it's not going to have enthalpy of formation because you don't have to form it. It's just the elemental form of it. Okay. Now we'll get more into this later. It can have entropy, which is a measure of disorder. So elemental substances don't have delta H, they don't have delta G. But they are going to have entropy because they're going to have a certain amount of disorder. Okay, so another thing, when you look at how you write these equations, you always write the coefficient for the product to have a value of 1. So here's a simple example. Let's say that we want to make aluminum chloride, okay, AlCl3. So I want to write the equation for the production of aluminum chloride from its elemental substances. Okay, great. We're going to react aluminum and chlorine gas. Okay? Elemental forms, aluminum and chlorine gas. And we're going to get aluminum chloride. Cool. Now we need to balance it. Oh, okay, right? We have AlCl3, Cl2, so what are we going to do? Morgan.
3 in front of the CO2.
3 here.
And then a 2 in front of the aluminum and the aluminum.
Okay? Balance, cool. Yay for Chem 1. Conservation of mass. Great. So this is the value associated with the production of aluminum chloride. So this is the equation. But I don't want a 2 in front of the aluminum chloride. I want that to have a coefficient of 1. So what are you going to do? Divide everything by 2. So this is Al plus 3 halves Cl2 yields AlCl3. Okay? So if you were to ask to write the equation for the formation of aluminum chloride in terms of standard enthalpy of formation, you just write it in terms of what it is. Now, like I said, you can do double displacement reactions, you can do synthesis reactions, there's a whole bunch of different ways to make aluminum chloride. But in terms of standard enthalpy of formation, you make it from its elemental substances. Now, if you look at AlCl3, if you go to this chart, you can look up the thermodynamic value of aluminum chloride. That's negative 705.6 kilojoules per mole. So, is this reaction endothermic or exothermic? You should not hesitate at all on this answer. Exothermic, why?
Negative.
Negative value. So what that means is this. If you did this reaction, you take a chunk of aluminum, you react it with green poisonous chlorine gas, you're going to make aluminum chloride. Energy is going to be given off in this process because here's what's going to happen. If you think about it, you got to break the bonds that hold the chlorine together. Okay? So you got to put some energy in to break the bonds. But then, if you notice, then you've got to make AlCl3. So you've got to form a bunch of bonds on the other side. So since you're just forming more bonds than you are breaking, you got to figure, oh, okay, great. You know, that's probably going to be an exothermic reaction because more energy is going to be released in the formation of bonds than in the breaking of the bonds. So sometimes you can just look at a reaction and go, okay, hey, I'm forming a bunch of bonds. If I'm forming more bonds than I'm breaking, odds are it's going to be an exothermic reaction. So if you look down that chart of the delta H's, you'll notice that the vast majority of them, not always, but the vast majority of those delta H's are negative signs. So the vast majority of times when you look at your enthalpy values, those are going to be negative values. Now, this is going to be important later on. This is for the formation, okay? This is for the formation of these from its elemental substances. But if I took aluminum chloride and decomposed it into aluminum and chlorine, said, oh, okay, right? And if I reverse this, I'm going to make that 3 halves. If I reverse it, instead of reacting aluminum and chlorine to make aluminum chloride, if I start with aluminum chloride and said, hey, I want you to break that up into aluminum and chlorine. If I reverse the process, what do you think it's going to be? Endothermic or exothermic?
Endothermic.
Endothermic. Because now you got to put a bunch of energy in, because now you've got to break a bunch of bonds. So if it's exothermic, sounds biblical, but if it's exothermic the way that it's written on here in terms of the formation, if you decompose it, you're going to switch to the sign. So if it's negative here, you're going to make it positive. If it's positive, you're going to make it negative. Okay. Now, I'm going to go through a very long process to show you how to work one problem. I am never going to expect you to do this, okay, ever. But it's important that you understand the theory. So I'm going to work this problem. It's going to be a big step, lots of steps, lots of math, okay? And you're going to sit there and go, oh my God, we're camp, woe is us, do we have to do this on the quiz? You don't even have to do it on an assignment, okay? But you have to understand the process, okay? So bear with me. You're never going to have to do this, but I want you to get the theory. So don't flip out and go, oh, big camp, this is so hard. Okay. So what we're going to look at is ammonia reacting with 7O2 as a gas to produce 4NO2 plus 6 waters as a liquid. Okay, so here's going to be the reaction. And what we're going to try and figure out at the end of the day is this reaction endothermic or exothermic. Now, let me kind of give you a visual. So I've got ammonia, NH3, okay? I've got 4 of these. That's going to react with 7 oxygen molecules. So when we get done, here's what's going to happen. You're going to end up with NO2. So you're going to get some action that's going to look like this. So you're going to make NO2. You're also going to make water. So you're going to be making 2 different things. You're going to be making NO2 and you're going to be making water. But you're going to be making liquid water. Okay? Now, I'm going to go through a big long process here, but understand why I'm doing this. So here's the first thing that you want to look at. On the reactant side, you have 4 NH3s. So what I want to do is I want to break that down into its elemental forms. So in other words, I said, hey, here's ammonia. I'm going to give you 4 of these, and I want you to break it down into its elemental forms. So what are the elemental forms when you decompose ammonia? Do not make this difficult.
Into an H2.
You're going to get what?
H2.
Hydrogen and
Nitrogen.
you're going to get N2, right? The elemental forms. You're going to get nitrogen gas and you're going to get hydrogen gas. So if you look at the math, and again, don't flip out. Just show me the process. So out of this, you're going to get 2 N2s and you're going to get 6 hydrogens. Okay? Everybody cool with that? All I did was, if I break this down, I'm going to get 2 nitrogen molecules. There's your 4 nitrogens, and I'm going to get 6 hydrogens. Okay? Cool with this. Now, the oxygens, they're just oxygen. Okay? I really can't break those down. They're just going to be oxygens. But now I'm going to recombine these. So I'm going to make my 4 NO2s. So what I'm going to do is I'm going to take some of the oxygen and some of the hydrogen, and that's going to combine to give me my 6 waters. And then I'm going to take some of the oxygen and react that with some of the nitrogen to get my 4 NO2s. So here's the process. The first thing I did is I deconstructed the elemental form, the products, I deconstructed the reactants into their elemental forms. Then I'm going to take the elemental forms of those and recombine them to get my products of NO2 and water. Okay? Got the process. I'm going to break them apart and then I'm going to recombine them. Got the visual. So now I've got this, my NO2s, and then I've got my water. So we're off to the races. Now, I need somebody with a calculator and to look up values in the book. So here's what we're gonna do. We've got the 4 NH3s. So what I want to look at is just the single process of decomposing the NH3 into 1/2 N2 plus 3/2 H2. So look in your book, find the delta H for the formation of ammonia. It's something around 50, I think.
Negative 46.19.
Negative 46.19. Now,
Okay.
kilojoules per mole.
Yeah, that's
Okay?
what yeah.
Got to know where this comes from. Now, here's the trick. That's for the formation of ammonia from its elemental forms. Okay, that's not what we're doing. We're decomposing it. So if we decompose it, what are we going to do with the sign of the delta H? Make that positive. So that's going to become a positive value because we're decomposing the ammonia. Now, that's going to happen 4 times. So what do you think we're going to do with the 46.19? Multiply that by 4. So somebody take 46.19 times 4. And don't round this number. Give me all the digits.
184.76.
184.76. Okay. So here's the significance of this number. Number 1, you'll notice that this is a positive value. Why is it positive?
Flip it around.
Because you're
Beyond that, just look at it in terms of breaking or forming bonds. I'm breaking bonds. I have to put energy into the system. I had NH3, right? Oh, come back here. I had NH3. I had to break the bonds that hold these things together. The only way I can do that is I put energy into it. That's why this is a positive value, because I'm breaking these bonds. Now, I don't have to worry about the oxygen, okay? Because the oxygen is the elemental form of this. I don't have to worry about that. Now, let's talk about making NO2. So, the reaction to make NO2, the elemental, out of its elemental form, is going to be 1/2. Oh, I hate this pen. Plus O2. Okay? Makes NO2. So look up the thermodynamic value, and this is going to happen 4 times. So look up the thermodynamic value for NO2.
33.84.
Positive or negative?
Positive.
33 point what?
84.
Okay? And that's going to happen 4 times, so multiply that by 4. What do you get?
135.36.
135.36.
0.36.
Now, notice that this is one of the few that has a positive delta H, okay? Most delta H's are negative. Now, we have one left, and that's the water, which is going to be H2 plus 1/2 O2, and this is vitally important that we're going to make 6 waters as a liquid. Not waters as a gas, waters as a liquid. So, Charles, what's the delta H for water?
Negative 285.83.
Negative 285.83. Okay. And that's going to happen 6 times. So multiply that by 6.
1714.98.
1714 is a good year, 0.98. Okay. Whew! Now we have all the numbers. Long process. So, somebody, if you've got these numbers, take the negative 17 that you just found, the 1714.98, add that to the 135.36 and the 184.76. So you get something around 1400, negative 1400.
Negative 1394.86.
Negative 1394.86 kilojoules per mole. So what this means is that this overall reaction, okay, the overall reaction out of this whole thing is the overall reaction endothermic or exothermic? Exothermic. Now, that's overall. I'm not saying you didn't dump energy into the system. You did put energy into the system in breaking the bonds. You also released a lot of energy when you formed a bunch of bonds. Now, obviously, this is a long and arduous process, okay? But I did this so you understand the mental framework of the process. Like, oh, okay, right. Anytime you have a reaction, you have to break the bonds that hold it together into its elemental forms. Then you go, okay, now we're going to recombine the elemental forms into making new compounds. That's the long process. Here's the short process. So this is what's on your equation sheet, and there's going to be 3 versions of this. So we're going to deal with this first one that says delta H, again, this is change in enthalpy. If you look at how this is written for the reaction, is the sum of the delta H's of the products minus the sum of your delta H's of the reactants. Now, notice that you have the same format, whether it's delta H, delta S, or delta G. It's always products minus reactants. Okay, there's no variation on the theme. It's always the sums minus the products minus the reactants. Always the same format. So, here's how this plays out. If you look at this reaction, how this whole thing started way back up here at the top. So the initial reaction that we had was this. Okay? 4 NH3 yielding 7 plus 7O2 yields 4 NO2 plus 6 water. So we're just going to do the shortcut process of this. Now, notice that this is sums. Okay? You don't have to switch signs. You just treat it as it is written in the table. Don't switch signs. Okay? The subtraction will clear that up. So I've got my products are 4 NO2s plus my 6 waters. So to use this, here's what we got. I'm going to have my 4 NO2s plus my 6 waters as liquid. I'm going to add all those together, and then I'm going to subtract the reactants. The only reactant that I have to worry about is my NH3. So that's going to be minus my 4 NH3s. Is going to equal my overall delta H for the reaction. Now, it's handy if you think this through, because sometimes what will happen is that we have like an algebra problem. So sometimes what will happen in lab, like you will know the delta H for a reaction, and you're trying to find one of the reactants or one of the products. So if you know what the overall reaction is, and let's say you know what the water is and you know what the ammonia is, you can solve then for the NO2 algebraically to get that value instead of reacting nitrogen plus oxygen to make it out of its elemental forms. So you can also go, hey, if I know the reaction, I can find algebraically some of the individual values. So here's how this is going to play out. So you got your 4 NO2s, and your NO2s is what, 46.19 times 4, plus your 6 waters. Your waters are, what was your waters? Negative 285.83. Minus, that is vital that you realize that is a subtraction. Okay, that is a subtraction. So then you got minus my 4 NH3. The NH3 was what? 4.76. Now, here's the deal. Bless you.
Thank you.
when you look at that chart, is your NH3 a positive or negative number the way that's written on the chart?
H3,
NH3.
negative.
So keep that as a negative. Don't switch the signs like, oh, but that's a reactant. This is why you subtract that negative with mathematically means you end up adding it. Okay? But that's why you keep that as that negative value. And that was what, negative, whatever the ammonia is, negative 46.19. No, your NO2s, I screwed that up. Your NO2s are 33.84. My bad. This is not going to end well. Hold on. Hold on. Your NO2 was, your ammonia was negative 46.19. So if you go through this, you're still going to get that exact same answer that we did up there. Okay? So that's why I said I wanted to show you the process. Process is you take anything as a reactant, you break it into its constituent forms, and then you take those elemental forms and you reconnect it. Now, here's the dichotomy of this thermodynamic chart. You have delta H, delta G, and delta F. Three exceptionally important thermodynamic properties. But the irony of it is that there is no way to directly measure any of them, okay? There are no enthalpy probes, there are no entropy probes, there are no delta G probes, okay? So we talk about them, they're vitally important, but there isn't a one of those that you can measure directly. What you do is you measure the impact that it has, like on the water. Oh, the temperature of the water went up. Cool, okay, that's an exothermic reaction. Boom, see what happens that, then you work your way back. Okay. Whew, that was a lot. I'm done. You're not, but I am.
All you have to do is study this tonight.
Oh, it's a book.
Yeah.
Oh, man.
Like, I'm going to really invest this time.
I've not finished it.
Yeah, you got a lot to do there.
I started it.
You haven't?
No, I haven't.
Okay, good, that's all.
I'm starting to say.
No.
I missed it yesterday, so I spent all last night studying for the
I use my time
Take
wisely.
it today.
I'm also gonna say.
She said she's not making it till
Oh,
Friday.
yeah, I have one.
So I
There's
studied
no
all
way Charles
last
has done
night.
that
I
with
know
me when he wasn't here.
We finally figured out what these actually
You sound
mean, you know,
very-
and how to do this.
Well, you still know stuff.
Friday.
Wait, hold on. Hold on, let me see if I can do it right.
I was like,
I don't know.
I was like, we're
I
talking
got
about.
69.
My dad was like,
What is
we're
that,
talking about
68?
magnetic.
68.
Other thing. We're talking about magnetism. Magnetism.
Magnetism.
Magnetism.
There you go.
Magnetism.
What did you
Physics.
call it?
Magnetism.
Yes.
Wow.
1, 2, 3, 4,
Magnetic.
Hey, I have autism.
Magnetism.
got one of them speech.
And stroke.
Speech.
No,
I just
so
can't talk.
geometry.
Words are complicated and shouldn't have that many letters.
Aren't you an AP, right? Or weren't you?
I am.
Oh, Rose is?
Yeah.
Charles?
You said you didn't get invited to your.
Yeah.
Yes.
That sounded like a hurt.
Yeah, so
How?
Okay.
It's the same.
There you go.
It is.
On 67, that's A and C, not A through
It's
C.
the arcade during school.
It's A and C.
You didn't get invited. Because he doesn't have.
Gold star.
I use it.